Thank you for coming. Thank you for coming also to the speakers. First talk today is a talk from Dr. Edgars Butanovs, which is leading research in the Institute of Solid-State Physics in Latvia. He has been working on gallium oxide for 4 years, and he has a special interest on the material as photodetector for deep ultraviolet because of the ultrawide bandgap. Well, and the floor is yours.
Thank you very much. It works, yes, perfect. On the laser pointer is this. Okay, thank you very much for coming to this seminar in the morning. And thank you for the opportunity to present here. My name is Edgars Butanovs. I work in a thin films laboratory, and as the title suggests, I mostly work on growth of the thin films, not that much on devices. And I will present our institute very briefly and our results, which we have obtained in the last 4 years on different techniques, how to grow gallium oxide. So brief outline, I will introduce my institute, where I work, Institute of Solid-State Physics, and our lab, what available infrastructure we have there. Then some brief words on gallium oxide. I don't know how many of you work on this material or not, but there's some interesting things to discuss. Then I will show some results that we have obtained with different techniques and the outlook with the future plans. All right, Institute of Solid-State Physics is located in Riga in Latvia. It's a kind of big building next to the river. There's a nice view on the trees and from the windows. It's one of the strongest innovation ecosystem player in Latvia. We do both fundamental research as well as applied research for companies, especially in materials research. So the institute was founded, I think, in the early 70s, and there are quite many different topics, starting from complex oxides, spectroscopy techniques, as well as organic semiconductors. In 2015-16, there was a new clean room built, 180 square meters, and over these 8-9 years, we have obtained some new tools, all the lithography tools and different prototyping tools there. Currently, I think these are not the most newest data. We are around 200 to 250 employees, of which a bit more than 100 is PhD researchers. These data are also a bit older. We rely heavily on different projects, so that's why we apply a lot to different calls internationally and nationally as well, and we try to attract funding for postdoctoral researchers and students as well. So our institute, the 5 main research pillars are materials for energy harvesting and storage, electronics and photonics, nanomaterials, theoretical modeling. We have a large supercomputer in our institute, as well as thin films and coating technologies. And today, our lab and me, I will talk more about these two, so materials for electronics and photonics, and it goes together with the thin films and their growth technologies. So briefly about our lab. So it was established only in 2017 by merging 2 different labs together to kind of condense the research. Of course, the labs have history before, and it's one of the leading labs at ISSP, especially for high strategic importance for research and development. So we do services for companies, deposit coatings for different applications. Head of laboratory, Professor Juris Purans. We have around 10 PhDs usually, and some students, doctoral students, master students, and 2 technical staff members. Since 2017, we have obtained 11 patents in our deposition technologies, which we develop, as well as published more than 95 papers since 2017. As I already mentioned, we kind of diversify our efforts, both on fundamental research and also as well as applied research. I am also reading a study course on thin film science and deposition technologies in University of Latvia. So we also have participate in educating a new generation of researchers in physics and engineering, and in this course we also do a lot of laboratory exercises, so students can have hands-on experience on all the deposition tools we have. So what kind of tools we have? So we mainly focus on 6 different techniques we have. Our kind of pride is this cluster tool, which is a cluster of I think 7 vacuum deposition chambers with both metallization tools, thermal evaporation, e-beam deposition. There are 2 sputtering chambers, some cleaning chambers, and all of them are interconnected with the glow box. So you can work with atmospheric sensitive materials to blow the substrate, clean it, do different processes by robotic arm transfer, and then package it outside in the clean room for work outside. Historically, our main focus is magnetron sputtering. We have working on that since basically 80s. So we have some refurbished old tools as well as completely new tools. I don't do magnetron sputtering myself. It's mainly my colleagues, but we are our research closely integrated in that. We have an MOCVD tool, which is a relatively old tool. I think the design is from the late 90s, and we bought it a bit used from a company in Germany in the late 2000s, and it was mainly used for gallium nitride growth. However, in the last few years, we are trying to rebuild it for work in gallium oxide. We had some progress, and now it's going much better. So I will talk about that a bit later. We also have a kind of CVD system that's for nanomaterials. I originally, back in the days in my PhD studies, I was working on nanowires and 2D materials. So we used this setup for growing those things. Pulse laser deposition is quite a new tool. We bought it a few years ago. We have 2 chambers, both for oxides and sulfides, as well as we also in our lab we have atomic layer deposition mainly for some device prototyping. And currently we are setting up a new roll-to-roll sputtering technique. So this is a research my colleagues do. So it's for smart windows. It's a large area deposition. I think you can use flexible substrates up to 40 centimeters wide. It's kind of semi-industrial tool which we'll use for R&D for different companies which they want to outsource. We have open access labs principle in our institute. So we have this management system where you can obtain a license for a specific tool, and then by adding your project or something, you can always access this tool and book the time. And it's very convenient to do research. So first of all, for our thin films characterization, we use electron microscopy tools. So scanning and transmission electron microscopy. We have, of course, the X-ray diffraction, fluorescence, XPS as well. Then we have quite many spectroscopy tools, ellipsometry, UV absorption, transmittance spectroscopy, photoluminescence, Raman infrared spectroscopies, as well as some other techniques specifically for thin films characterization. And some of this we do ourselves, the work, and sometimes we collaborate with other labs in our institute. And more recently, we have obtained some device fab techniques in our clean room. So we have optical lithography, direct laser writer, mask aligner. We have electron beam lithography. Very recently, like 2 years ago, we also obtained a dry etching tool. We are still learning to use it. So yeah, that's the main tools we use in our lab to fabricate the devices. But the main focus on our lab is growth, not really device fab, so that we do kind of on the side. So here are the main topics in our lab which we work with. It's first of all what I already mentioned, large area chromogenic coatings. So these are coatings for let's say windows, mainly. Yeah, if we put some coatings on, we can improve the efficiency of the buildings. Regarding the thermal exchange and something like that. So we have big running projects on that, but that's mostly work on my colleagues. And what I do with some of my students, it's ultrawide bandgap semiconductor thin films. So we work on gallium oxide, and we worked a bit on spinel zinc gallite. And mainly we do it for UVC photo detection, and as well now we will collaborate here in our SAFEPOWER project with regarding for power electronics. Also, what we did some work on antiviral and antibacterial coatings. We had some projects running during the COVID time. We developed some interesting materials there. I also work on the side a bit on superconductive thin films. And back in the days, we worked a lot with nanomaterials. It's more fundamental study, both on growth, making different heterostructures and nanostructures, and then also we study their nanomechanic properties. But okay, let's switch more to the physics side. So gallium oxide. It's a not very new material, but I think in the last 10 years, it has emerged as a really promising candidate for power electronics, firstly, and also for UVC detection. It has 5 polymorphs. This beta monoclinic phase is the thermodynamically most stable. However, the other ones are also interesting. For instance, corundum phase, and it has a band gap around 4.6 to 4.9 eV. So it can be used for solar blind detection, as well as it leads to quite high breakdown fields in power devices. And regarding other competitors, which you probably all know, gallium nitride, silicon carbide, it has some benefits, mainly for high voltage capabilities, probably not that much for high frequency applications due to low thermal conductivity. But still, yeah, it's interesting for wind turbine inverters and solar panels, etc. Other thing I'm interested in is solar blind UV detectors. So since we have quite a wide band gap, we can start detection in this range around 200 to 240 40 nanometer wavelength. So competitors there is Algan, but it's still kind of expensive technology, and it has, I think, a bit smaller band gap. And here, I think with Algao, with alloying gallium oxide with aluminum, we could obtain very nice UVC detectors. What are the main challenges of gallium oxide? First of all, it has lack of decent p-type conductivity, so most of the devices are limited to metal semiconductor junctions or metal insulator semiconductor junctions, and that means if we want to have a PN junction, we need to make it from a hetero. We need to put another material on top of it. Other issues are, of course, it's challenge of field management, so selection of specific dielectrics for gallium oxide, as well as point defect control that I think it's now a bit more understood. So monoclinic, it's a very low symmetry phase, so there can be a lot of different defects, and they appear there quite easily. As a grower, I know how complex it is to grow very high quality gallium oxide. Other thing, a lot of people, now less, but a few years ago, they were saying, oh, the bad thermal conductivity is a technology stopper for gallium oxide, but as I've seen in the latest conferences, so it's really more about engineering issue, how to do the architecture of the device, not that much as a really technology stopper. So there are some ways how to extract heat from gallium oxide. As well as, in my opinion, interesting topic is stabilization of other phases. As I mentioned, this metastable corundum alpha phase, it has wider band gap, so there's some interesting possibilities there to explore, and it has not been explored that much. I will briefly mention also such a material as nickel oxide. It's a wide band gap material, so its band gap is around 3.6 to 4 eV, and it's a p-type material. As people have shown already in the last, let's say, 3 years, it has first of all, nice band alignment with the gallium oxide. What is good from technological perspective, you can get decent p-type mobility at low deposition temperatures. So sometimes you can work on 200 degrees, 300 degrees, so it's relatively cheaper. You can do it with a sputtering or pulse laser deposition. And it's native p-type, so you basically, by tuning oxygen defects, oxygen partial pressure during the deposition, you can optimize this p-type conductivity. And I just basically yesterday evening I checked the new results. So this slide was made 1 year ago, and here I had 4.5, I think, kilovolts. And in 1 year, from a Peartone group, they have basically this May published a paper on 13.45 kilovolt breakdown fields. So mainly it's about device architecture, how you limit different these breakdown mechanisms. And I think it's very nice to see how far it's went. And I think this nickel oxide, gallium oxide has a very high potential in a power devices. And there is this very nice, if you're interested in material, nice review paper last year, which accumulates a lot of knowledge on this heterojunction. So if you're interested, I suggest read this. Another, I already mentioned twice, I think, this corundum gallium oxide. So it has a slightly wider bandgap, wider bandgap than a beta phase. What is nice, it's a higher symmetry material. So typically it's prone to less defects in the structure. However, since it's metastable, it's hard to grow with classical methods or classical approaches. So what people typically do is they use some more kinetic processes, so mist CVD. That's an interesting technique Japanese kind of demonstrated, and now it's being employed quite nicely. It's a high growth method, similar to this halide vapor phase epitaxy. This is also possible to grow alpha phase gallium oxide. However, if we talk about classical methods, I don't think I've seen MOCVD growth of alpha phase gallium oxide, but you can induce this phase growth by epitaxial stabilization. So you can do it with pulse laser deposition, MBE, with physical methods, let's say, and also sputtering. And typically you need to select a very nice lattice matching substrate. And the best is M-sapphire. It gives the best results due to specific growth mechanism, how this alpha phase growth on grows on corundum sapphire. I will talk a bit more about our results as well, so there'll be more details. What other benefits are of alpha phase gallium oxide is, first of all, alloying with aluminum. So if we want to alloy the thermodynamically stable monoclinic phase, there's quite big limitation. You can go up to like 25% or something until it gets very bad, to say the least. However, if aluminum oxide, is corundum, so it's the same crystalline structure. The lattice mismatch is not that big, so there's some demonstrations. By growing it alpha phase, you can alloy it basically up to 8.6 EV. There's some demonstration, I think, for Cornell Group in the US on this, as well as some interesting results of alloying with iridium. So there are very few papers on that. That's from, I think, Kaneko Group in Japan. So they use this mist CVD. And what is nice, iridium can induce possibly p-type conductivity. That's at least what has been demonstrated. However, what the issue is, it's quite an expensive metal, so not many groups work with it. But could be interesting to explore if possible. And the last thing before I move to the results, it's some interesting thing about Schottky diodes and what I've noticed in the last few conferences I went to. It's very interesting to make Schottky diodes with noble metal oxides, such as platinum, iridium, which I already mentioned. So they're quite good results, I think, from very simple device structures. If you deposit slightly oxidized this, let's say I will talk about iridium oxide. If you deposit slightly oxidized Schottky junction, you can get quite good results in, let's say, in electric field capabilities. These are quite recent results, so it's a very fresh thing. And in our institute, we have expertise. We have iridium sputtering target, which probably we have it from since Soviet times. And I think this block we have, it costs like some 30,000–40,000 euros. So we plan to investigate a bit this iridium oxide deposition, study a bit more what happens at the interface at different oxidation levels. Maybe in a collaboration with you to see what kind of devices we can fabricate from this relatively simple structures, and maybe advance it further with some nice field management, etc. Okay, so what we have done so far in our institute. So I already mentioned some things. But mainly we work with both beta phase and alpha phase thin films. We do some a little bit N-type films with PLD. We do amorphous gallium oxide for UVC detectors, and we plan to do some more heterojunctions. And I'll briefly mention we have collaborators who do DFT calculations, so that helps from understanding some basic defect structures. As well as we worked on this spinel, interesting spinel materials in gallite. There is some possibility of bipolar doping by controlling these so-called antiside defects in spinels. And it's interesting for power devices, but it's not been explored that much. Okay, so I will start with less interesting results. So we work with all the methods I mentioned before. So PLD is more we use for comparison. It's interesting for, let's say, testing, but usually the nice uniform films are on very small substrates. It's like 8 by 8 millimeters. So for really device fab and repeatable studies, it's not that nice, but it's interesting for fundamental exploration. Let's say this alpha phase epitaxial stabilization. Tried a lot of things. We do some prototyping for devices, some simple devices for UV detectors. We explore different epitaxial growth orientations, etc. And we also a bit work with this P-type nickel oxide. We can deposit in the same chamber both of these materials without breaking the vacuum. So that's kind of recent work. We haven't done very interesting results yet. Then we'll move to MOCVD. So this is kind of interesting. We can do epitaxy on 2-inch substrates. So that's already something more interesting from the device perspective. For now, we have worked only on sapphire substrates. So it's heterota epitaxy, and unfortunately, beta phase gallium oxide does not match very well with this aluminum oxide. So there are still quite a lot of defects. It's a kind of large, there are these large grains. However, there's the small angle grain boundaries, which really kind of ruins the electrical properties of the material. We worked on developing different buffer layers or different nucleation layers, similarly as back in the days was done for gallium nitride growth on sapphire, to induce these kind of thicker buffer layers, and in the end you have a real device layer, which has much less emissive dislocations, etc. So we developed a similar process for gallium oxide, improved quite well the crystalline properties of the films. However, still, it's if you take a look from like rocking curves or something like that, it's not good, but it's close to the state of the art on the heteroepitaxial films. So in future, it would be interesting, of course, to do homoepitaxy, because that's the only way how to get really device grade films. And yeah, we are, this is null tool as already mentioned, and we are reconstructing the reactor to match oxide processes because it was designed to have a nitride process, gallium nitride. What is bad with oxide processes in MOCVD, there's a lot of parasitic reactions, so chemical reactions that happen not on the substrate surface, but just in the above the surface. So that leads to typically lower crystalline quality of the film. So we're implementing some novel solutions how to mitigate these parasitic reactions. Okay, and then the sputtering part. Sputtering is what we have explored the most. We have developed a novel technique based on liquid gallium target. I will show some more details what we have done. We can obtain very high deposition rates. So this is mainly at room temperature, so it's interesting mainly for amorphous films. We can do co-sputtering, so we do this with the zinc. I will also show you some results. And our capabilities, we can also, which is not very common for sputtering systems, we can have substrate temperatures up to 800 degrees, which is nice to obtain kind of highly crystalline films. And typically our developed DC process has much higher deposition rates than ceramic target sputtering, this RF, which is commonly employed for gallium oxide. Okay, so we developed a specific container, since metal gallium melting point is around 30 degrees. So typically in realistic sputtering conditions, it will be in liquid state. We have developed a specific technique how to sputter a liquid metal. It's very nice. We can get very high deposition rates, decent crystallinity. There's some defects from the bombardment. We are fine-tuning the process, so these results were on higher. The power, if we do the lowest deposition power at very slow rates, it's much nicer crystallinity. What we also explored, we explored alloying with zinc. So we have gallium target here. We also use zinc target, and we could obtain different types of, first of all, zinc alloyed gallium oxide or solid solution, zinc oxide alloyed with gallium, and as well in specific conditions, we could obtain very nice spinel phase zinc gallate. And we studied what is nice with our system. We have this so-called plasma optical emission spectroscopy. So we can monitor zinc and gallium proportion in the plasma, and we can do the feedback loop to the power controller. So in real time, we can adjust, the computer adjusts the sputtering power depending on the composition of the plasma. So it gives very nice uniformity in the films. And then this is kind of very nice state-of-the-art tool for co-sputtering of the films. This is, I didn't change. This is we have it already published in the spring, I think. Another thing I already mentioned that we studied from the sputtering perspective is alpha phase thin films. So M plane is kind of a bit well known to use, but we can also use A plane sapphire. So what typically happens, people use C plane sapphire. So it's this 001 cut. Is the most common thing, and if you take a look here, this -201 famous beta gallium oxide orientation, it aligns very well with this C plane orientation. But if we take a sapphire with other planes, so usually M or A works, we have very nice epitaxial match with alpha phase gallium oxide. And if you do very nice growth process, you can stabilize this metastable phase even at higher temperature. And what we explored first of all impact of the substrate temperature. So it was kind of in the beginning counterintuitive that you elevate the temperature of the substrate and you stabilize a metastable phase. So it should kind of logically be the opposite. If you increase the temperature, it should move to the thermodynamically most stable phase. It's kind of opposite. So the beta phase disappears and the alpha phase appears at higher temperature. This is mainly probably related to, first of all, diffusion. So the deposition rate is slower. So there's more time to have this epitaxial stabilization, let's say, to find the atoms, to find the correct positions on this substrate. That's one thing. I think that's one of the main reasons. We also studied the thickness dependence. So what we noticed, if you have thicker films, there's mixture of both alpha and beta phase. And typically when you have thicker films, it's easier to stabilize this alpha phase. And then we did TEM study to see how it looks like. Let's take a look here. So at 700 degrees, what we obtain is some islands of alpha phase nucleation. And then when you have some exposed facets of other orientation, not the favorable one for alpha phase growth, the beta phase grows probably away from these exposed edges. However, when we increase the temperature, we can see that we only have alpha phase growth up to some nice thickness. Here it's like nearly 300 nanometers thick. This is A plane sapphire. It's not the best, but there's some completely new results. On M plane sapphire, I think we can grow up to 600, 700 nanometers, which is close to state of the art what I've seen in literature on the thickness of the alpha phase layers, except mist CVD, I would say, but I'm not sure if I've seen very thick films. And so quite an interesting result, and we want to see what we can do with these alpha phase films. In parallel, what we don't do, but what our colleagues from our institute do, we have a very strong theoretical group with the DFT calculation. So in the initial stages of the project back in the days, these are results, I think, from 2021, 22, when the gallium oxide defects were not explored that much. They studied a lot these all different types of monoclinic defects, well, mainly vacancies, oxygen vacancies, some interstitials, some nice papers, very well cited from our colleagues. What we recently did also some interesting, we did some experimental work. It did not match kind of very well the theory. Partly some Raman spectroscopy did, but it's hard to do correctly the experiment. So we put some iridium inside. So if you grow monocrystal, single crystal gallium oxide in iridium crucible, there might be some contamination of iridium in the film. It's mainly in Czochralski growth. So what we discovered, it inhibits p-type conductivity. So if you want to obtain some for n-type, there's also kind of some not that nice defects. But typically, so you shouldn't grow. Takeaways, you shouldn't grow really beta gallium oxide device grade from Czochralski. So nowadays, I think they do floating zone thing. So that's kind of already not that relevant, I guess, but there's some nice theoretical results from that. Okay, I think that was quite quick. Yeah, so I will go to the outlook of my talk. So yeah, our main goal now is to finish our MOCVD reactor. Hopefully, will be up and running in the spring, so we can do very nice doped film epitaxis. So we mainly studied growth until now, not really semiconductor doping levels, etc. So we plan to do that next year. We still are exploring nickel oxide. So this is interesting for heterojection with gallium oxide. For now, we are playing around with PLD, but we will develop the whole nickel oxide process with a controllable charge carrier concentration and mobility levels. So proper semiconductor process with sputtering. Also, we are exploring alpha phase growth. And we will do some, hopefully soon, some feasibility tests for silicon implantation. I have samples with me. We plan to do, one of the first things is this iridium oxide Schottky diode with gallium oxide. We will probably discuss it with the colleagues here, how to proceed with that. We have the capability to do it, and we can, I think there's still a lot to do in this field in general, because yeah, the promising results are basically from this year and the last year. And for me, it's also interesting. We are pursuing this amorphous gallium oxide. It's more technological process for real commercial devices. So amorphous gallium oxide and aluminum gallium oxide, they are promising for UVC detection, mainly because the process is cheap. You can do large scale and you can get decent quality detection. So we are pursuing that as well. All right, thank you very much for your attention. I want to acknowledge, of course, our new project, SAFEPOWER, for the opportunity to be here, and I would be very happy to answer any questions you have. Thank you very much.
Thank you. Questions? I mean, thank you very much for your. It's been a very interesting talk. I mean, you have made a very good overview of your institute. I think it's actually brilliant.
Thank you.
So, any question?
Thank you very much. And in your opinion, as a gallium oxide expert, how do you see the, let's say, competition between diamond and this kind of materials or device applications?
If you talk about emerging materials such as diamond, diamond is very tricky to grow. From growth perspective, first of all, to have it in real world applications, first of all, you need a single crystal substrate, and then you need the thin film growth processes. And I think for diamond, it's quite tricky already to do that, both things. So it's hard to say. Diamond, I maybe in far future, when some new methods are discovered how to grow it nicely, that there might be some competition. Of course, it's an excellent material. It's amazing material from the theoretical properties, but for now, I don't see how it's possible to grow it in such a high quality to reach these values. Regarding the other materials, the established gallium nitride and silicon carbide, as we heard in May in Berlin, there was this gallium oxide conference, and there was the industry people there talking about the perspectives. So I think the industry has put so much money into silicon carbide and gallium nitride. They don't plan to switch gallium oxide now, maybe in 10 years. Even the results are very promising. I think the industry is not ready to switch to new material based on the investments they have made in the last, let's say, 10, 20 years in this field. But probably Mike will comment more on this on the device perspective. I can only comment on growth and yeah.
Okay.
Very nice talk. My question is more directed towards vertical power devices. How many times should we wait to have gallium oxide with enough quality for doing vertical power devices?
Well, you mean in general or from me?
You can say it in general, and after from you, why not?
Yeah, in general, I think there will be quite a lot of demonstrations already, and there are very nice progress there. I think it's in labs. It's been demonstrated already.
For high voltage? 10 kVs or something like
10
that?
kV, I'm not sure that much now. It's just
It's I mean, our crystal technology, that's
1
1
kV.
1 kV.
yeah, 1
And
kV.
it's
So
still,
yeah.
I mean, I see demonstrations about 4 kV, maybe maximum.
Mhm.
So right now, lateral topologies, it's the best choice.
No, I think people
Yeah.
want to.
Yeah, they do vertical, yeah.
But it's tricky.
Yeah.
Yeah, and they're waiting, of course, for larger wafers, everything. From my perspective, yeah, it's a matter of the buying substrates. It's quite expensive to buy these mono, of course, to fine tune your process specifically for home epitaxy, everything. So it requires some investment. But when we have demo CVD running, we can, of course, investigate that as well. Yeah. Yes.
Thank you for a nice talk. I have 2 questions about the gallium oxide. I don't have any idea about this material. And I wonder, what's the difference in terms of electrical properties of the amorphous gallium oxide? Because you talked about this phase.
Yeah.
What about the amorphous?
Amorphous,
layers?
well, let's say it's conductive. You can
It's
quite.
a lot.
It's relatively conductive, I would say. It's the oxygen vacancies, I think, which contribute in quite decent n-type conductivity. Of course, you know, there are a lot of defects. Amorphous, all of it's basically defects.
Yes,
So
but this is not so in all materials.
yeah,
Let's consider
yeah.
silicon
So
dioxide.
yeah. So there is this famous IGZO, I think, this famous amorphous semiconductor people use in transistors even. And then some LED devices. I think, yeah, I don't forget. Yes, in Japanese group, Hosono group, yeah, they have developed amorphous semiconductor technologies. For some materials, it works quite nice. For us, we are mainly aiming for UVC detectors, so we have some decent conductivity and it works quite well. The problem is due to many defects, it's the response time of this. There are a lot of trap states, so charge carriers get trapped, and typically these detectors are not the fastest. So you need to fine tune these properties of these films based on your application, let's say.
And the other question is about the technology possibilities you have in your lab. It's about the ALD system. Which sort of materials are you budgeting?
Yeah, so it's a very basic commercial system. So we have aluminum oxide, hafnium oxide, zinc oxide. I think the classic standard options. So nothing very interesting. That's a commercial option.
The substrate
Size, I think it was up to 6-inch substrate. Thank you. Yeah.
This was a nice talk. The topology here of the deposition. What is the size of the substrate? And if it's very homogeneous, and if you can keep the substrate, is a reactive position or is a reactive position?
Yeah, so it's unfortunately, yeah, the substrates, if you want a thickness homogeneity, typically it's 8 by 8 millimeters. These are small substrates, and we have some issues if we want to get decent growth rates. Yes, the thickness uniformity, it's not excellent. That's why I use it mainly for some testing, something like that. We do direct deposition. We don't have off-axis options, but typically our system, we don't have much droplets issues, something like that, and we can go to up to 800 degrees. Yeah.
Yet I forgot to ask about what's the thinnest layer? Are you able to?
Or which material we can?
Oh no, in the gallium oxide, the most common you have to work.
Yeah. So
I missed that. So,
thinnest or thickest?
sorry?
Thinnest or thickest?
No, the thinnest.
Thinnest.
The
Well,
smallest.
yeah. So it depends on the method, because MOCVD typically it starts with the island growth, so you don't get uniform film first. Then you have the nucleation, and then it grows together. So there it's probably tens of nanometers. With a physical vapor deposition technique such as sputtering and PLD as well, we have islands. But sputtering, I think we can get few nanometers. It's slightly there. Of course, we will have more defects in this first layer, but probably we can do a few nanometers.
I'm not at all on your field, and please could you explain what is exactly behind the growth stabilization or epitaxial stabilization? It's only a matter of adjusting machine parameters, or is there something else in the more theoretical?
Mainly, it's the choice of the substrate. So the good thing is the aluminum oxide and gallium oxide corundum phases are quite well lattice matched. So the thing is, you need to compete between the thermodynamics and between the kind of the substrate on which the bonds arrange in the correct fashion. What we noticed, we can grow, for instance, at 800 degrees nice alpha phase. If we put it in another furnace, heat it up again, it will start to transform to beta phase. So that's the thermodynamics where it takes into account. What we need to do to have this epitaxial stabilization, we select the optimal substrate with a very nice lattice match, and we grow very slowly, so all the atoms arrange themselves to this substrate. And if you do it slowly enough, you give it the process time, it will arrange layer by layer, basically this how it should be. This thing is, we still don't understand why it works so good with sputtering, because sputtering induces defects, and then when you have defects, you should disrupt this nice alpha phase growth, and you should have a beta phase again. Because from MBE, I would understand it's a nice layer by layer process. You should get very nice films, and that's what I've noticed. Here in sputtering, maybe it's more competitive between the thermodynamic process and between some kinetic processes. We don't know. Maybe it's related to also the growth rate, because MBE, for instance, they grow thinner films. They're of high quality, but they're limited. Usually, what I've seen in papers, they don't grow thicker than 200 nanometers. So it means it's not only about the epitaxial, this coping the crystal structure, but it's about some other processes we don't know about. So I would assume it's some kind of balance between how fast you deposit and how slow you deposit. Some middle ground, I guess. Yeah, it's hard to understand yet. But it's very interesting, I agree.
We were talking about the low quantity changes, but what about the preparation process?
Yes, then. It might be crucial, since sputtering induces some damage, usually to the substrate and to the film. Maybe it's crucial in the first initial layers that there is some damage. Typically, we don't do any extraordinary cleaning procedures. We do some very basic cleaning and then put the wafer inside, and it works for us. We, of course, could do a lot of studies in the first initial stages, how the islands form. Maybe it's related that there's no island formation, probably. The islands are very small initially from sputtering. It's not big islands, and then we don't have these exposed facets of the grains. So maybe that's related somehow to this.
Okay, I think we should move to the next talk.
Thank you very much.
For your nice, very nice presentation.
Thank you.